right, good morning, everybody. Everybody have a good weekend? Unit 1's closed out. Anybody not get anything done? I mean, didn't anybody missing anything in Unit 1? Good, because I have to start figuring midterm grades. It's going to be figured on Unit 1. And I'll have to tell you how many points that's possible with Unit 1. I'll try and do that on Thursday. But it'll be based on everything on Unit 1 that was due, okay? Today we get to start Unit 2. Unit 2 is going to cover biology of the nervous system, sensation, perception, and the learning chapter. Now, when we are talking about the biology of the neural system, actually we're going to be talking about the biological aspects of psychology, and the nervous system will be included in it, because we are going to be covering the endocrine system, and we'll cover a couple of things that may be outside the area of neurobiology. Okay, first thing is we need to kind of set a foundation. There are two types of nerve cells. Now, many of y'all have probably heard of one of them, the neuron, but the other is called glial cells. Now, glial cells are extremely important. They help neurons communicate by directing their growth. They help keep the chemical environment stable. They provide energy. They secrete chemicals to help restore damaged cells. They release chemicals that influence neurons. They respond to chemicals from neurons, and they change in response to experience. Now, all those things tell you how important glial cells are. This always does this, and I'm sorry. Come on. Okay, these are glial cells. Now, some of these slides are really neat, because when I was in undergraduate school, we didn't have access to some of the detail that we have now on these slides. So all those things that I just said about glial cells, and here's a picture of them. Probably the most important thing I'm going to tell you is this next slide. Without glial cells, neurons cannot function. This is a neuron. This is another nerve cell. Now, neurons, they are a completely different cell than other cells, but yet they have some similarities, okay? Now, they have a cell body like other cells. That's called a soma, S-O-M-A. They have a cell membrane like other cells. They have a nucleus like other cells, and they have mitochondria like some cells. That's the similarities to other cells. But what makes neurons different than other cells? First of all, they have these little branch-like structures, numerous branch-like structures that carry that receive messages from other neurons. Okay? You have a bunch of those. You have one axon. At the end of the axon are little bulb-like structures. They have a ton of names for this little bulb-like structure. They're called axon terminals, they're called vesicles, they're called terminal bulbs, telodendron. We'll see a bunch of these names. A lot of names for the same thing, and those little vesicles are the place where neurotransmitters are stored. Neurotransmitters, they're chemical messengers. We're going to go into those in a few minutes. Also, you've got this fatty protein that covers the axon, and the substance is called myelin, and when you have it covering an area like that, then that's called a myelin sheath. So, you've got dendrites, bunch of dendrites. You've got the axon, one axon. You've got the terminal buttons or vesicles that store neurotransmitters. Neurotransmitters, they're chemical messengers. You've got the myelin sheath. Myelin is a fatty protein. We'll talk about that in a minute. Then it's similar to other cells in it has a cell body, a nucleus, a cell membrane, and mitochondria. The cell membrane is what's called semi-permeable. That means it's going to let some things in and some things out. But it's not going to let everything into the cell, and thankfully, it's not going to let everything out of the cell. This is another picture of a neuron. This is astounding. Such a beautiful picture. Here's your nucleus. All of these are your dendrites. You've got these little things here are the messages that are being sent. Now, here's another picture that is awesome. Oh, nuts. I was all set to really astound y'all. Okay, here we go. This is an awesome picture. And the reason is, first of all, you can see very much what the nucleus is. All those spaghetti-like structures, dendrites. But here's what's neat, is you can really, really identify the axons here. That's an axon. Let's see here. There's an axon. This looks like the axon here. The what?
That one that you just touched.
This one?
Mm-hmm.
That's an axon, yeah. Looks like the axon may be coming off this one, and this one's out of sight. There's an axon. Okay, so you have one axon. You have a bunch of dendrites. The axons send messages to other neurons. The dendrites receive messages. Okay? Anybody in here a really, really good football fan? Very knowledgeable about it? Got a question for you here. You've got the quarterback, right?
Yeah.
All right. He's underneath the center, He takes the ball and he gets into the pocket. All right, now he's looking, he's really excited, he really wants to let go of this ball in a pass, and he can't see any eligible receivers, but the center is open. Why can't he send that pass to the center?
Because he's blocking.
But he's not blocking anybody right there, he's all by himself.
He can't touch the ball.
Why is that?
Because
Once the quarterback catches the ball to throw it, he can't run out to do it. He has to pass it.
Okay, so is there a name for that?
if he touches the ball,
No, that makes him where he can't touch the ball?
it'd be called illegal touching.
Illegal touching, or what would he be called?
Which person?
The center. Like an ineligible receiver?
Yeah.
All right. Axons, they're the quarterbacks. Okay? They've got that message. It's really excited. It really, really wants to get rid of that message. But it can't send it to another axon because it actually is an ineligible receiver. But dendrites are all eligible receivers. And so that axon is really looking for a dendrite because that dendrite is looking and saying, here I am, come on. You can send it to me, okay? It's really, really, the more that I learn about this stuff, the more excited that I can get. It's really, really an awesome thing. Neurons, they come in different shapes, different sizes. They share common structures, okay? They will share common components such as dendrite cell body, axons, end bulbs. Those are all common to neurons. The number of nerve cells in your body is estimated to be as high as 1 trillion. I believe that is actually low now. We're going to see a film very shortly, and I think he ups that. Similarities to other cells: cell body, cell membrane, nucleus, mitochondria. Differences: the axon, dendrites, vesicles, also called terminal buttons. The dendrites receive impulses from other neurons. The axons, they will vary in length, okay? This is going to be based on the site of the neuron. They carry electrical nerve impulses from the cell body to the end bulbs, okay? These end bulbs are also known as terminal bulbs, terminal buttons, teledendrons. So we're even adding more names to the same structures. They're also called vesicles. The neuron operates by electrical activity. It has a negative charge of approximately minus 70 millivolts, and that's when it's resting. Neurotransmitters, these are chemical messengers. Okay? Now, let's say this is an axon, this is a dendrite. There is a space. When they line up, there's a space there. That's why I was making an analogy of a pass. and not a handoff. Because these two do not touch when they communicate with each other. This space is called the synapse. Sometimes it will be referred to as a synaptic gap. The space between the cells. Okay? Now, neurotransmitters, they're chemical messengers. They relay information from one nerve cell to another. These chemicals cross the synapse so that the molecules can attach to receptor sites on the dendrites. Now, this neurotransmitter activity is chemical in nature. Okay? Now, their action can be excitatory or inhibitory. Incitatory means it's moving the receptor neuron to firing threshold, or inhibitory, making it harder for the neuron to fire. Their actions can be summated and eventually fire, as opposed to operating on the all or nothing principle, which is the case for the neuron. The exact number of neurotransmitters are still unknown. Psychoactive drugs tend to work at the synapse and can alter or suppress neurotransmitters. Now, I'm going to do a disclaimer right away. I'm not an AMP instructor, and this is a very, very simplified explanation. I was taught, this is called the lock and key theory or explanation of what goes on. Now, the terminal bulb becomes very, very excited. When it becomes excited, it releases the neurotransmitters into the synapse. Now, the synapse, or the neurotransmitters, they don't stay in the synapse. They look for a place to lock into. These are called receptor sites. So here, they find a place and lock into it. And now, the dendrite starts doing its thing. These that are left are basically sucked back up into the terminal button. And that's called reuptake. So they just don't sit around and float and disappear. They go back into the terminal button. Now, let's say that instead of this type, I've never had this illustrated by, with music before. Nice little touch. It should have been something more like the Space Odyssey, you know.
I was thinking
Bom,
Cosmos.
bom, bom. All right, so let's say that these are the types of neurotransmitters. All right, it gets excited, and now these neurotransmitters are in the synapse. But remember, these receptor sites were for a different type of neurotransmitter. But these find these receptor sites, and they decide to go in those sites themselves. So they hold that place. Now, here at school, they've given me two different keys. Look at that, they're almost identical. Look very similar. This is the one to my office. I came in this morning, I took this key, I inserted it into the lock, I turned it, I was able to proceed into my office, and I started doing the work I needed to do. Okay? That would be like the T being locked into this. That was the right key for the right lock. But the other day I had my hands full. I couldn't look at my keys real fast, or real good, so I grabbed one and I inserted it in the lock. It fit perfectly. I went, oh, rats, okay? Now, it could stay there all day, but it won't do a thing because it's not the right key, okay? It's not gonna cause any kind of reaction. It's not gonna do anything. It just sits there, okay? That's the V. This receptor site is not made for that neurotransmitter. So if it gets in here, it's not gonna cause any kind of reaction. But when T comes, all kinds of things are going to happen, okay? Does that kind of make it a little easier to understand what happens here at this part of the cell layer or cell? Space between the cells, called the synapse. We've talked about that. Neural activity is electrical, synaptic activity is chemical. Big difference. Important point. Neural activity is electrical, synaptic activity is chemical. Well, then we have a thing called action potential. A minute ago, I said that the cell membrane of the neuron is semi-permeable. It lets some things in and some things out. Sometimes what happens is a positive charge is going to be pumped out. And nature does not like an imbalance. If you've studied chemistry, you know that a stable molecule is one that has the exact same number of positive charges and negative charges, okay? So, this is now not a balanced, stable membrane. You have positive charges out here, and the negative charges are wanting them back in. Things around, the environment around the cell membrane and changes within it can cause this membrane to become excited. When it gets excited, it can reach a point that they have these little gates in the cell called channels. When it gets excited, this little gate can swing open, and that positive charge rushes in, and then this gate shuts real quick. That causes this area of the membrane to become very excited. That channel or gate opens, this rushes in, and all the way down now, it fires all the way down. It continues all the way to the end. Okay? Now, it's very, very fast. And as soon as one gate closes, another gate opens. And there's no way that I could even mimic how fast this happens, but I think I can give you an idea of how those gates open and close, open and close, open and close. I want you for a second to imagine yourself at the Razorback game last weekend. Good game. All right, you're watching all the play on the field. And you're really, really into that play and you're really excited about it. But then you notice across the field, somebody has started the wave. And so you see the wave and it's starting to come around. And you're watching the game. Come on, Hogs, pour it to them. We need a win. And the wave's coming. And it's coming around, and you're watching this, and you get more excited about the football game, but yet you're getting more excited about this too. And so you see the wave coming, and your turn's about ready to start. And so, yeah! Okay, now we can go ahead and watch the game. All right, and so you're back into the game, and you're really into it. Go Hogs, go, woo pig, and all this. And the wave's making its way around, and you're keeping an eye on it. You're watching the game, and it's coming back around, and you're still rooting for the Hogs, but you're keeping an eye on it, and here it comes. Yeah! All right, and then the one right next to you does the same thing. And the one right next to them does the same thing. And all the way, just up, down. See? There we go. That's what we're talking about. Well, I don't want to forget anything, don't want to misrepresent it, so let's go over the notes and make sure I told you everything about it. Membranes are semi-permeable. They allow some things in and some things out, but not everything in and not everything out. Cells pump positive charged molecules out through the membrane. This makes the inside of the cell slightly more negative than the outside, so therefore it's called polarized. Many of these positive charged cells are kept out by the cell membrane, but they will enter through special openings called channels. These are located in the membrane. The neuron operates by electrical activity. It has a negative charge of about minus 70 millivolts when it's resting. It will operate on the all or nothing principle. That means that a stimulus is either strong enough to cause the neuron to fire or it's not. If it's not sufficient, not strong enough, the neuron will not fire. When the neuron fires, the electrical impulse will travel from the cell body toward the terminal buttons. It will only travel in one direction. When the impulse reaches the terminal buttons, the neurotransmitters will be released. So, when you have this, when they start with the placing or opening of channels and going all the way down, if one starts, they all do it. Okay? It's not one can get lazy and foul up the whole thing. Okay? They all do it. So we say that it's an all or nothing or all or none kind of action. We also say that the neuron fires. We liken it to a gun. If you take a gun and you pull the trigger and that chemical reaction starts within that cartridge and that bullet starts ejecting out of that cartridge, out of the gun, we can't stop it. Once that chemical reaction starts, that bullet's going to take off. So it's either going to be a dud or it's going to fire. And the same way with a cell, with a neuron, okay? These channels act as gates. They can be opened or closed. Normally they're going to be closed, but changes in the environment around the cell can cause the gate to open and allow positively charged molecules to rush in. When this happens, the next area of the axon becomes depolarized, causing the next gate to open. This sequence creates a wave of change in the electrochemical potential that spreads all the way down the axon. This is called action potential. Okay? Once it's happened, it's said to have fired. It's all or nothing. Now the speed is going to be consistent within the cell. But each cell has their own speed. Okay? So, let's say I have a little Volkswagen. And it's got a little flaw. When you turn it on, when you put it in gear, it's either in neutral and doing nothing, or when you put it in gear, it's going to go 70 miles an hour. Boom! Every time, it's going to go 70 miles an hour. Okay, I can depend on that cell to do 70 miles an hour, I mean that car to do 70 miles an hour. But then, I have a friend of mine who's got a Lamborghini. And lo and behold, he's got some kind of same glitch in his car. It's either in neutral doing nothing, or when he puts it in gear, it's going to go 150 miles an hour. Now, every time he takes off, it's gonna be 150 miles an hour. Now, we're both cars, but my little Volkswagen can only do 70 miles an hour, but his consistently does 150 miles an hour. So, the speed is consistent in both of our cars for our cars, but it's different than the other car. Does that kind of click with y'all, or am I mixing y'all up? Is anybody not following what I'm saying? Are you getting it? Because you kind of had that glazed look over your face like you were not connecting. Okay, okay. The speed is consistent, but the cell, per cell, but it will vary from neuron to neuron. It can be anywhere from 0.2 meters a second to 120 meters a second in speed. That would be 360 feet a second. I think that's right. A meter is approximately 3 feet. 3 times 1, yeah, about wouldn't that be like almost the length of a football field? 360 feet, 300 feet's a football field, isn't it? Because it's 100 yards. I'm just asking, I'm trying to get an idea about how fast that is.
You're not wrong.
Huh?
You're not wrong. You're not wrong.
Oh, thank you. Please tell my husband that, because he always says that I'm a 0 in math. We've talked about myelin. Myelin, protein, it's a fatty protein substance. Its function is to speed neurotransmissions. Now, I'm challenging my art prowess today. Now, this is a very poor representation, but I'm trying to get the concept over to y'all. If this black is myelin, and it is to speed the neurotransmissions, what would happen if something compromised a little of the myelin sheath like that?
Throw off the pattern.
Do what?
You will throw off the pattern.
How would it throw? You're absolutely right. One more step, and you got it. What would happen to that neurotransmission? Somebody said something. It's going to slow it down. Absolutely. Let's think of it this way. We're going down I-30, all right? And we've got all these lanes like that. And then they decide they're going to do some construction. All right, so now they put all the barrels. We're famous for our barrels. All right, so they have all these barrels, and you've got all these lanes that have to merge into half of the space. There's going to be a bottleneck, and it's going to slow this traffic pattern down. Same way here. Now, it's going to slow it down. What would happen then if the entire myelin sheath there is compromised?
Well,
The what?
it's really dead. It's basically gone. Dead. It's sort of way.
You're right, but what would it do to the neurotransmission?
Slow it down.
No, slowing it down was this. You're on the right track. It would stop it. Because you've got it going right here, but now it can't go any farther. And so it stops right here. There is a name for that disease. MS. When a doctor is diagnosing MS, one of the things that's brought to them at the very first are symptoms. I have a friend of mine who has MS, and she started complaining, first of all, about her vision started becoming tunnel vision. She didn't have peripheral vision, okay? So he started looking, and then she started developing some other symptoms. Now, knowing that we're dealing with nerves, and knowing that we're dealing here with a problem with her sight, what nerves do you think might be impacted that the MS would be affecting?
Optical.
Something in the optical system. Very good, very good.
I took it out of any physiology, so.
There you go. Now, she also, over the years, has developed what's called a lazy leg. Okay? And she will take a step, and she has a cane, and then she'll have to, like that. And, I don't want to be on camera, I'll do this. When she gets in the car, she has to lift her leg to get in the car.
Basically, it's like
It's heavy.
heavy.
It's not dead, it's heavy, because she still can move it, she still has function, but it's heavy. That would be where it's not a complete compromise of the myelin sheath, okay? A loss of coordination is called ataxia. We usually refer to this when we're talking about leg function. Okay? So if somebody's having a problem walking, they usually say, well, they're ataxic. Okay. We're going to be talking about the nervous system. Okay? The nervous system is divided, the human nervous system divided into two separate branches. The central nervous system and the peripheral nervous system. You want to find out that as I'm talking about this, it's going to go in twos, okay? So, the human nervous system divided into the central nervous system and the peripheral nervous system. The central nervous system divided into the brain and the spinal cord. The peripheral nervous system, let's go down here, it's going to be divided into the autonomic and somatic divisions. Okay? The autonomic has two parts, the sympathetic and the parasympathetic divisions. The somatic has two types of nerves associated with it, motor nerves and sensory nerves. This is easier for y'all to see now, okay? The human system is divided into two branches. The nervous system is divided into two branches, the central nervous system and the peripheral nervous system. Peripheral nervous system divided into two branches, the somatic with the afferent and efferent nerves, motor and sensory, and the autonomic divided into the sympathetic and parasympathetic divisions. The central nervous system divided into the brain and the spinal cord, those two divisions. Now, This is a human brain. We're going to be studying several structures of the brain. We are not going to go in real depth, okay? We are going to study what's called the corpus callosum, the thalamus, the hypothalamus. This is the midbrain, this is the pons, this is the medulla. We also study lobes. So, first of all, we have different ways of designating reference to the brain depending on what you're going to be talking about. The brain is broken in or divided into two halves. These halves are called hemispheres. You have the right hemisphere and you have the left hemisphere. Whenever you are talking about anatomy and physiology, biology, anything with medicine and such, we use what's called the anatomical position. The anatomical position is like this, okay? When we refer to the right, we refer to the patient's right. So this is my right hemisphere. When we refer to the left, it'll be the patient's left. This is the left hemisphere. Left lung, the right kidney, okay? It's always the patient's. That way, there's no mix-up in records and in communication. Like one doctor says, well, we got to remove the right leg, and something happens and he can't do it, and so his partner comes along, and he's talking about the patient's right, and the other surgeon says, well, the right leg, and he's using his right, and he amputates the wrong leg. I mean, that's a big no-no. So there has to be a standard, and the anatomical position is the standard. Okay, this is going to be the left hemisphere of the brain. All right? This is an illustration of the spine. When we are talking about the spinal cord, it is protected by 24 bones called the vertebrae. These vertebrae, they stack on each other in a way that it forms a little cavity in the back, and that spinal cord goes up through that cavity, and therefore it's protected this way very strongly toward the front, and then you've got these little spiny things that protect it toward the back. I'm going to bring a model of a vertebrae to y'all on Tuesday. Back injuries are bad. Spinal cord injuries can be devastating. The higher the injury, the more dangerous it is. If you were to sever your spinal cord low like that, it would probably cause paralysis in the legs. You get a little higher, it could have a quadriplegic, where you have paralysis in the arms and legs. Or if you get it way up there in the neck, not only would they be quadriplegic, it would affect their breathing. Those neck nerves are connected to the diaphragm, and if you've got, the brain sending the right signals, and you've got the spinal cord, but it's severed, that message goes right there and stops, and the rest of the messages don't get through. So the brain says, okay, diaphragm, do your thing, we need to breathe. Diaphragm doesn't get the message. So that's why a lot of quadriplegics have to have a ventilator to breathe for them the rest of their lives. I don't know if y'all know the guy that played Superman in the 1970s. He was out horseback riding. He fell off his horse, broke his neck, and he was a quadriplegic for the rest of his life. Each vertebrae is separated by a spongy-like substance called a disc. You want those discs because it cushions these bones from sitting on top of each other. If they were to sit on top of each other, they would grind. And they grind that spine down to nothing. And also you would have bones sitting on nerves, which would be excruciating. Now, I have a friend of mine who loves motorcycles. Absolutely loves motorcycles. One day his wife called him up and said, let's eat at such and such a restaurant for supper tonight. He said, I think that's a great idea. He gets on his motorcycle, he heads to meet her at the restaurant. He's going down this back highway, long line, moving very, very slow. He's an impatient guy. He doesn't see any reason for them going slow. It looks clear, so he takes his motorcycle, wheels it out, guns it, vroom, like that, and about the time he got to the front car, he found out the car had been signaling that they were going to turn left. Right as he got there, the car started turning into him. To avoid it, he swerved and he launched himself into a culvert. They had to med flight him, and when he got to the emergency room, instead of having his neck aligned like this, it was aligned like this. Now, his spinal cord was not severed, which is amazing. They said that the way that thing was lying at that moment, that it could cut the spinal cord at any moment. They needed to go in, do an operation, realign the neck. He was in surgery for, seems like it was 6 or 7 hours. And then what they did was I think they took out all of his neck bones and they put a cage in there. And they put the spinal cord in this cage. When he went in, he had full mobility of all of his limbs. When he came out, he was a quadriplegic. His spinal cord was still intact. They said they had no idea why he was not coming back and losing that quadriplegic status. He finally did regain use of his arms. They at first said, we don't expect any real significant progress for 6 months because that spinal cord has been so insulted, it's extremely bruised and swollen, and it has to have time to recover. Well, several years later, he has use of his arms, still a paraplegic. But we got notification about a year ago, and it showed him on a treadmill, and he was trying to use his legs. That was like after 10 years of after his accident. I haven't heard from him to see where he's at right now, but he had started regaining feeling in his feet, and he was actually on a treadmill trying to move his legs. So there's so much we don't understand about the nervous system. We don't understand, the brain is probably the most complicated and miraculous thing on this earth. And we understand a lot of it, and yet we understand very little. The peripheral nervous system is composed of two branches, somatic and autonomic. The somatic makes contact with the environment. It transfers information from the senses to the central nervous system. It's voluntary, and it has two types of nerves associated with it. Afferent nerves are the sensory nerves. Efferent nerves are the motor nerves. Some people pronounce it afferent and efferent. I was always taught afferent and efferent, okay? Afferent nerves are your sensory nerves. They carry information from the receptors, from the sensory receptors, to the central nervous system. I'm very sad to announce that they don't have Krispy Kreme donuts anymore on Bowman. Not only because I like Krispy Kreme, but because it was an excellent way for me to give an example. It used to be that I could drive down Bowman, and I was just happy as a lark listening to a radio, and then all of a sudden, these Krispy Kreme molecules that are in the air are inhaled, and they go to my olfactory sensors, and the message is carried to the brain, and I open my eyes real big and say, oh, Krispy Kreme, yum. Well, the brain says Krispy Kreme, oh, that tastes good, we want some Krispy Kreme. So it sends a message through the motor nerves to the muscles, and it says, turn, and I go, and it says, go in and buy. And so I get out of my car, I march right in, I order my donuts, I pick them up, I buy them, all because of this part of the nervous system. Okay? So the afferent is going to carry the information from the receptors to the central nervous system, and the efferent is going to carry messages from the brain and spinal cord to the muscles. The peripheral nervous system, the second part is called the autonomic part. It's composed of the sympathetic and parasympathetic divisions. The sympathetic division, it's what initiates a condition called fight or flight. We now call it fight or flight or freeze, but we're going to just talk about fight or flight today. It will mobilize the body. It gets the body ready for danger or extreme stress. Okay? I am walking in the forest, I look up and I see a very large grizzly bear. My heart is going to start increasing and pounding. My pupils are going to start dilating, letting more light in. My palms are definitely going to become sweaty. My breathing is going to become irregular. My gastric activity is going to stop. Glucose is going to pour into the system as well as adrenaline. And at this point, I have to decide, am I going to stand and fight or am I going to run? In that particular scenario, unless there's somebody right next to me that I can outrun, I'm probably SOL. But the body has prepared me for that emergency. The body has geared me up. The heart racing, pupils dilating, palms sweating, breathing faster, irregular, gastric activity inhibited, glucose poured into the system. You get a surge of adrenaline. It's this condition that we hear about things like a woman coming in. All right, here's a good example. I have a real good friend. She came home and the gun safe had fallen on her husband. Big, heavy gun safe. She screamed and she picked up the gun safe and pushed it off of him. Now, normally she couldn't do that, but because of fight or flight, she was able to. We hear these kind of miraculous type of actions that are done in response to emergency situations because of what the body does in this situation. Any questions? Well, you know, the question might be, well, why don't we just stay in fight or flight all the time, and that way we're ready for any emergency? It's hard on the system. Your system can't stay geared up like that all the time. And so as soon as the emergency is over, the parasympathetic division kicks in. It calms the body after the danger passes, returns it to a balanced state called homeostasis. Okay? It calms the body, returns the body to an equilibrium, returns the body to a balanced state, a state called homeostasis. Questions? This is really, really important stuff. Very rarely do I give you an assignment over the weekend. I want you all to not only review what we have talked about today, but know the nervous system and all of its branches. When we come back on Tuesday, I expect you all to know all of the branches, okay? Anybody got any other questions? In that case, I hope you all have a fabulous weekend. Enjoy, relax, and have fun. Study your nervous system, and definitely keep it legal, okay?
Okay, so my